Hi everyone, I want to continue our work in this video with hypothesis testing. So far we've discussed how we can set up hypotheses. Once we've collected data, how we can calculate a test statistic. And then we introduced the notion of a p-value, which is one way that we can assess the statistical significance of our data. And there are different ways that we can calculate p-values. We've seen how we can use null distributions in some cases. In this video, I want to talk about how we can use permutation tests to calculate p-values. And so to motivate this example, I want to return to an example we've looked at in class. And so this was an example for what's called the unscrupulous diner's dilemma. And so a lot of us have been in the situation where we go out to dinner with a number of people, and sometimes to save time, we just divide the bill evenly amongst everybody at the table, regardless of how much they order. And in some cases, people prefer to pay separately just for the items that they've ordered. And so these researchers were curious as far as whether people had different ordering habits based on whether they knew the bill was going to be split evenly or whether they knew that they were going to pay separately. And in particular, in this study, the researchers wanted to test, they thought that people would order more food and beverages when they know that the bill is being divided evenly. And you can imagine how this same behavior would have some implications in like environmental protection. Why do I need to recycle if all of my neighbors are going to recycle? And so with this goal in mind, here's how we could set up hypotheses to perform this test. The null hypothesis would be the boring claim that people order the same amount of food no matter how the bill is divided. So mu sub even is denoting how much the mean amount ordered by everyone when the bill is split evenly, and mu control would be the mean amount of food ordered by everybody if everybody was just paying for what they ordered themselves. So this is what we're considering the control. So the null hypothesis, this is the boring claim. We use parameters when we state this, and we use inequality as well. The alternative would be what the researchers here were trying to prove, which is that people are going to order more when they know the bill is divided evenly. So stating this in terms of our population parameters, we've got mu even minus mu control. This should be strictly greater than 0. So the alternative will have some sort of inequality over here. In this case, we choose greater than because the researchers wanted to prove that people were going to order more when it was divided evenly. Now that we've got our hypotheses set up, let's go ahead and consider how we could collect some data, calculate a test statistic, and then calculate the p-value of that test statistic. And so although this example, these hypotheses came from an actual study, for the purpose of this video, I'm going to consider a smaller set of data. So this is not the actual data from that study. So let's imagine we have 8 volunteers, and we're going to split them into 2 dining tables that each contain 4 people. So one of the tables is going to pay evenly. One of the tables is going to pay, each person is going to pay for what they order. And we're going to assign these 8 people to these 2 tables completely at random. And so in this case, let's just say we pick person B, C, E, and H get randomly picked. They get put in this table, and they're all going to order food, and then they're going to divide the bill evenly. These 4 people then get put in the control group. And a reasonable test statistic for this example would be, well, if we want to gauge which of these 2 claims seems more plausible, let's go ahead and take a look at the corresponding sample means. So sorry, I had even and odd numbers on my mind. This should be a subscript for the control group. So we calculate the mean amount ordered on the even table. So this, in other words, would be the bill divided by 4. And then we calculate the mean amount ordered by this table. We would add up, each person pays differently. We'd add up all 4 bills and then divide it by 4. And so let's say, hypothetically, again, this isn't actual data. We collect some data, and it goes like this. So the evenly divided table, well, one person ordered 15, 8, and so on, and then they would add up these amounts and then divide it by 4. Whereas this table, each of these 4 people pay for just for what they ordered. And so in this case, our corresponding test statistic of this sample would be the mean from this table, which is $11.23. The mean for this table, which is $8.67. So over here, we could see that the table that split evenly, well, they did pay more. And so the question is that a lot more? And that's a complicated question. Well, that's good. That's why we're all in this class. This takes some more sophisticated analysis. So we can calculate the p-value as a way of gauging whether this is a lot, whether this is extreme or not. So let's consider what could we do here. So in the previous cases, we were claiming something about the underlying population, and from that we were able to set up what's called a null distribution. So in this case, we don't know what the distribution is for this parameter, for the difference in these two means. So how can we calculate how bizarre this difference is if we don't know what the underlying distribution is? And so let's recall what the p-value measures. The p-value measures what is the probability of getting a sample as or more extreme than the sample we collected if the null hypothesis were true. And so although we can't set up a distribution using the null hypothesis, let's consider what the entire sample space of possibilities are here. So we have 8 people, and we want to split them into one group of 4 that pay evenly, one group of 4 that are going to pay separately. So how many possible ways can we pick these samples? So let's first ignore the fact that we don't care the order in which they're placed at the table. So person A, B, C, and D all placed at the table. First, let's consider that as a different placement. And if we first picked D, then picked C, then picked B, and then picked A. Although in the end, those are going to be treated as the same setup, let's first just ignore that and consider how could I pick a table of 4 people from 8 volunteers? Well, the first person, we have 8 choices. Then we have 7 for the second person, 6 for the third, 5 for the fourth. So that gives us 1,680 different ways I can pick 4 people to sit at the table. But of course, we do want to take into account that we don't care the ordering that they're sitting at the table, for example. It's the same for people. So for each setup of 4 people, how many different ways could we organize those people? Well, first I have a selection of 4 people. The second person I have 3 to choose from, and then 2, and then the very last person would be uniquely determined. So that means for each collection of 4 people, there are 24 different ways that we could order them. And we want to treat all 24 of those ways the same. So altogether, how many different setups do we have? Well, we would take all of these possibilities and then take into account that for each one of these setups, there's 24 equivalent ways of writing them. So that gives us 70 possible ways that we could have assigned these 2 groups. And so if you're thinking, I feel like we learned a way that we can calculate these more directly, that is correct. We did discuss this. So this is exactly equivalent to if we had used that 8 choose 4 formula. And in fact, the reasoning that we have up here is exactly where this formula comes from. For example, we could take this and break it up into the 8 factorial over 4 factorial, which gave us the numerator. And then we divide that by 1 over 4 factorial, which is taking into account that we don't care about the ordering. And in the end, whichever way we do it, we're going to wind up with there's exactly 70 ways that we could have assigned these 8 people to those 2 tables of 4 people. Okay, so where are we in this problem, in this analysis? So we have a test statistic. Again, sorry for the odd here. We have the evenly split table versus the control group, which is the table that pays separately. And in our data set, which was not the actual data, the difference in the mean amounts ordered at these tables was $2.56. And the question is that a large difference or is that not a large difference? We shouldn't just be making this decision based on our gut. So we thought about what's the sample space here? What are all of the possible ways that we could have split up these 8 people? And out of these 70 possible ways, how many of them are as or more extreme than our observed sample? And so in this case, 70 possibilities, that is actually not too bad. This is a pretty small data set. And we could actually list out all of these. And so over here, it's not too important what's going on. We're going to be using R to create these in class. But what's happening is here's our original data set. And here was the difference that we observed, the 256. And now we can go through and think about different ways that we could reshuffle. So what if we switched this person and this person? Here's another distinct way of setting up those groups. Here's what that difference would be. Look, this difference is not more extreme than ours. So in our case, a more extreme difference would be any difference which is more positive than 2.56. Because remember, we're doing a one-sided test here in the sense that our alternative is we suspected the even pay group orders more than the pay what you order group. So we would go through this list and try and identify what are all of these 70 possibilities. So this isn't all of them. There's a whole bunch more. And I'm just going to count every time I get a hypothetical sample that had a difference that was even as or even more extreme than ours. And if you go through this systematically listing out all 70 possibilities, then what you'll see is that there are exactly 7 out of the 70 that had a test statistic greater than or equal to 2.56. So that gives us 7 out of 70, in other words, 0.10. So there would be a 10% chance of getting a sample as or more extreme with a difference in the mean amounts equal to or greater than 2.56. So although we didn't have an underlying distribution to work with, we were able to list out the entire sample space, compare our difference to all of the other possible differences that we could have observed, and from that calculate the p-value. And there we go. You didn't even know it. We just did a permutation test. And so on the last slide, I just want to generalize the process for doing a permutation test. And so depending on what sort of test we're doing there, we might need to tweak this process a little bit. So I want to outline in general how we perform what's called a 2-sample permutation test, since we'll have some cases where we have matched samples. So in this case, we have 2 independent samples. One of them is size M, one of them is size N, and these 2 samples don't need to be the same size. So you can think of this as a treatment group and maybe N as a control group. And so what actually happens when you're doing a study is you put out a call for volunteers, and then you get a bunch of volunteers, and then you randomly select M of them, they're say the treatment group, and then you put all the rest of them in a control group that has size N. And in actuality, the researchers, they only get one chance to do this, and they collect the data from the one way that they split up these groups. And so with a permutation test, we're going to simulate what happens if these researchers in theory could have done this over and over and over again. So what would that process look like? So at first, we get all of these volunteers that come to our survey, our study, and there's M plus N of them. In our previous case, these happen to be the same. Generally speaking, that's not going to be the case. And then we randomly pick the first M of them to go into, say, a treatment group, or they go into one of our groups. And we're going to pick this without replacements. So we're going to pick a person, they can't be picked again. So all of these people are going to be placed in either group 1 or in group 2. So after we pick the first M people to go into group 1, then we take all of the rest of the observations and they go into group 2. I'm calling these people, but these could be any type of observation. Then we calculate the difference in some relevant statistic. In the case that we looked at, it was what was the mean of group 1, what was the mean of group 2, what's the difference in those two means. We'll sometimes see that we might be working with proportions, and this process can be extended to look at all different sorts of statistics. So then we repeat this process over and over and over again. So we do it one time, we calculate the corresponding test statistic, and then we would say, what is the next possible outcome in our sample space? What is another way that we could have split up these volunteers? And we do this over and over and over again until we get many of the outcomes. And what we'll see is that you can imagine how many different ways there could do this if we had 2,000 volunteers and they're each getting put into groups of size 1,000. That would be an insane amount of things to try and write out, and it would be incredibly difficult to determine when things are in fact distinct samples. So rather than worry at times about getting all distinct possible outcomes, we're just going to resample this process many times, and hopefully we'll see that that's going to be a good enough approximation for the p-value. And so once we've generated a whole bunch, say 100,000 possible samples, then we look through all of those samples and look at how many times did we get a statistic which was as or more extreme than the one way that we were able to split up these groups. And we calculate our p-value by calculating the number of times that we got a sample as or more extreme divided by the total number of resamples that we included in this analysis.